Hi everyone, welcome back to MATA35. In today's lecture in 9b, we're going to be going through a review of complex numbers and how they're related to rotations. So you guys might wonder why we care about complex numbers when this is a biology class, and even negative numbers oftentimes aren't that useful. Like, you can't have a negative number of bunnies. But it turns out that complex numbers have this property that they're related to rotations in higher dimensional space. And when you do a matrix transformation on some of these population vectors, they'll look something like a rotation, and so we do need to use complex numbers in order to characterize them. The first thing is, though, let's talk about what a complex number is. Let's see. So, it turns out that there's this really important property of real numbers, which is that there isn't something called algebraic closure. Now, what is this? This is a fancy math term for saying that occasionally you have equations that you don't have solutions to. So, for example, if we had x squared plus 1 is equal to 0, well, if you were to draw that out, if you were to draw out the parabola for y is equal to x squared plus 1, let's say this is y and this is x. So if you were to draw that out, you'll notice that there is, well, no intersection with the x-axis. So x squared plus 1 is never equal to 0 when you're working in the real numbers. There are other examples of this. For example, there's also no real solution to x squared plus 2x plus 2 is equal to 0. And when you draw that out, that looks, so that's actually a little bit shifted. Hopefully I shift this in the right direction. And this is equal to y equal to x squared plus 2x plus 2. And that also doesn't intersect. So also no intersection with x-axis. So now, what is this property of algebraic closure? Well, algebraic closure just means that every polynomial, p of x, has a real root, p of z is equal to 0. But clearly this is not true for real numbers. I should mention for r. So this is not true for real numbers. Now, what if you want to have this property? Because sometimes it's nice to be able to write down an answer to something, even if it isn't in the domain that we care about. So, what do we do? Well, what mathematicians do is we just imagine up a new number. So, I mean, I'm obviously heading towards imaginary numbers here, but let's imagine up a new number. Let's start by defining a solution to x squared plus 1 is equal to 0. Well, you might say, well, x squared plus 1 is equal to 0, and so x squared is equal to minus 1, and so x is equal to plus or minus the square root of minus 1. Now, this doesn't exist as a real number, but we can define this magic new number called I, the imaginary unit, to be equal to the square root of minus 1. Well, this has a couple nice new properties, but the most important is, well, len, when we plug it in, I squared plus 1 is equal to square root of minus 1 squared plus 1, which is equal to minus 1 plus 1 is equal to 0. So we're happy. And you might also notice that minus I also works. Plus 1, which is equal to minus square root of minus 1 squared plus 1 is equal to minus 1 squared times minus 1 plus 1 equal to minus 1 plus 1 is equal to 0. So now we have plus or minus I are solutions to x squared plus 1 is equal to 0. Now, why is this useful? This is useful for a couple of reasons, one of which is that you now have a solution to this. The other is you can actually now factor this irreducible polynomial by saying x plus I times x minus I is equal to 0. So that's an equivalent formulation. And this has some very nice properties because it means that basically we can factor everything out. How do you find that the square root of minus 1 squared is minus 1? Oh, but that's just by the definition of a square root, right? So a square root is the opposite of squaring. So if you take a square root of something and then you square it, well, that's by definition the opposite of it, right? And so what we've done is we've defined a new number. So we've created a magic new number I that has this property that when you square it, you get minus 1. Now this is a little bit weird, but this is something mathematicians do all the time. Sorry, I don't understand what word you wrote there. So I relaces? No. So I replaces the square root of minus 1. So I is equal to the square root of minus 1, and that is by definition. That is some magic. All we're doing is everywhere you see the square root of minus 1, we can replace it with the letter I. And like I said, this isn't a real number. We've imagined up a new number. And this is the whole point of I, is that it is something brand new that isn't a part of any ordinary real number system. But now, once we have this I, this imaginary number, well, since it's a number, we want to be able to add, subtract, multiply, and divide with it, like with any other real number. Like with the real numbers. It's not a real number, but we want it to have the same sort of properties as these other numbers. And that, of course, means that not only I is a new number, we also have a bunch of other numbers. So, for example, 2i, 3i, 500i, pi times I are all numbers. They're not real numbers, but if we want I to be a number in some fancy system that we're talking about, which we're going to name the complex numbers, well, then all these other things also have to be numbers in this new system. So now we have so that's multiplication. We also want subtraction and addition. So 1 minus I, 2 plus 4i, etc. And also the slightly more complicated ones, like 1 over I should also be a number. 1 divided by 1 minus I. 2 plus 4i divided by 1 plus 200i. So these are all numbers. These are all complex numbers in this new system. Even, as we'll learn later, the square root of I and e to the I and I to the I are numbers. And we call all these new numbers the complex numbers. So we call all these new numbers the complex numbers because what we've done is we've introduced a new number, and then we've said we want all these ordinary operations like addition, subtraction, multiplication, division, even square roots. We want all of those to also give you a number in this new fancy system. And it turns out that for complicated reasons, which I won't go into in this lecture, every single complex number, so all those numbers I showed on the previous slide, including the square root of I, or like I to the I, all of those things can be written in the form a plus bi, where a and b are real numbers, and I is, of course, defined to be the square root of minus 1. Although let's see a couple of these, just to show that we can convert these all into the standard form. So, for example, 1 over 1 minus I, well, this is going to be equal to, so we have a question. Complex numbers and imaginary numbers meaning the same thing. Not quite. So imaginary numbers are numbers that only have an I and don't have where a is equal to 0 in this a plus bi. Complex numbers you can include both a equal to 1 plus 2i and things like that. So complex numbers are a combination of an imaginary number and a real number, is one way to think about it. But yeah, so we have 1 over 1 minus I, and let's say we have, if we take this and we multiply it on both the top and the bottom, so because this is a fraction, this is going to be 1 minus I times 1 plus I, and 1 plus I on the top. If you multiply this out, you end up getting 1 plus I divided by 1 minus I squared, right? Because you can just multiply I out, and you do a binomial expansion, you multiply that, you get 1 minus I squared on the bottom. But note that this is equal to 1 plus I over 2, right? Because I squared here is negative 1. And so 1 minus negative 1 is equal to 2. And so this is equal to 1/2 plus 1/2 times I. Okay, so even though we started out with 1 over 1 minus I, we can rewrite it in this form a plus bi, where a and b are both real numbers. And let's give a more complicated one. So I won't, we'll get into how to derive this a little bit later, but let's try the square root of I. So now, you notice that earlier we had the square root of minus 1. That wasn't a real number, and so we had to do something fancy. We had to introduce a new number in order to create a number system that had the square root of minus 1. Naively, you might think, well, maybe the square root of I also isn't an imaginary number. But it turns out that luckily, the complex numbers have this property of algebraic closure, and the square root of I is also another complex number. Now, what does it mean to take the square root of something? So this means a number z such that z squared is equal to I. Right? That's the definition of a square root. It means that when you take the square root and you square it, you get back the original number. I'm going to try something. I'm going to try 1 divided by the square root of 2 plus 1 divided by the square root of 2I. So clearly this is a complex number. How we get this number, we'll talk about in a little bit. But so we have this number, and when we take the square of this, 1 divided by the square root of 2 plus 1 divided by the square root of 2I, when we take the square of this, well, we can pull the 1 divided by the square root of 2 out front. So this is equal to 1 divided by the square root of 2 times 1 plus I, and this entire thing is squared. So this is equal to 1/2 times 1 plus I squared, which is equal to 1/2 times 1 plus 2I plus I squared. But notice that I squared is just minus 1, and so 1 plus I squared is equal to 0. So this is equal to 1/2 times 2I, which is equal to I. And so this is indeed a square root of I. And as an aside, there are often multiple square roots. So as an aside, minus 1 divided by the square root of 2 minus 1 over square root of 2, I also works. And this brings us to this important property that I've been hinting at this entire time, which is that the complex numbers have algebraic closure. So this is a fancy way of saying that if you have this new number system with these complex numbers, any non-constant polynomial has a root in C. So basically, anytime you can write down x squared plus 2x plus 2 or whatever, that has an answer that is an imaginary number, even if the coefficients are other imaginary numbers. And let's go ahead and show this. So you might have x squared plus 2x plus 2 is equal to 0. You can solve this a couple different ways. Let me solve it by completing the square, since that's a little bit more intuitive. Plus 1 is equal to 0, right? So I'm just splitting the 2 up into a 1 plus 1. And so therefore you get x plus 1 squared plus 1 is equal to 0. X plus 1 squared is equal to minus 1. So x plus 1 is equal to plus or minus I, because we're taking the square root of both sides, and the square root of minus 1 is I. And then therefore x is equal to minus 1 plus or minus I. Or you could just use the quadratic formula. So the quadratic formula also happens to work. So you get minus 2 plus or minus the square root of 4 minus 8 over 2. So then x is equal to minus 1 plus or minus the square root of 4 of minus 4 over 2. And so x is equal to minus 1 plus or minus I. And it turns out that any formula you can write down, any polynomial formula you can write down, has a root in the complex numbers. So, and it turns out to be even stronger than that, because you can actually completely factor out any complex polynomial in terms of monic factors. Okay, so this is just a really fancy way of saying that once you introduce this imaginary number I, then you can solve these equations that you couldn't before. But, okay, I've done all this fancy algebra, but what does it all really mean? Well, luckily, because you guys have taken a linear, well, not a linear algebra class, but you guys have had a brief introduction to linear algebra, we can use the tools from linear algebra to understand a plus bi. So, since a and b are both real numbers, we can think of the point ab as a point in the plane. And this is a way that we often represent a plus bi. So let me draw out so this is what we normally call the complex plane. So one axis here is the real numbers, and the other axis here is the imaginary numbers. And so you might have, well, this is 1, this is 2, this is 3, and this might be I, 2I, and 3I. And this is minus I, minus 2I, minus 3I, and minus 1, minus 2, minus 3. Okay, so what might a point be? So, well, you might have a point here, which is 2 plus I. Or you might have a point down here, which is, let's say, minus 2 minus 3I. So every point, every complex number you can represent as a point in this complex plane. And if you think about it from a linear algebra point of view, well, you have this 1 here. 1 in the complex numbers is basically this vector 1, 0. And I in these complex numbers is basically the vector 0, 1. And so something like 2, 1, well, that is 2 plus I, which is equal to 2 times 1, 0 plus 1 times 0, 1. Okay, so basically every single point in the complex plane you can think of as, well, every single complex number you can think of as a point in this complex plane. Now, I'm going to take a brief moment and give you guys some pictures of bunnies and birds. So what does this all have to do with biology? Well, when we were talking about population sizes, even negative population sizes were considered meaningless because we can't have a negative number of animals. So you might wonder, what does it mean to have an imaginary number of bunnies and birds? Well, that is also really not particularly meaningful. However, these imaginary numbers play a role in other parts of understanding population sizes. So remember, we had this entire linear algebra section, where matrices are transformations of vectors, right? So matrices, some of them scale the vectors, some of them stretch and squash them, other ones rotate the vectors, remember? And for the stretching and scaling operators, we were able to characterize those in terms of their eigenvalues, because their eigenvalues determined how much they stretched or squashed things. But we mentioned as an offhand comment that when the eigenvalues are imaginary, other stuff happens. And this is when the eigenvalues are imaginary, the thing that happens is rotations. So for example, this rotation matrix here, so that's 0, minus 1, 1, 0. We can compute the eigenvalues of that. So that's the determinant of lambda minus that matrix. So lambda 1 minus 1 lambda, the determinant of that is equal to 0. So lambda squared plus 1 is equal to 0. And this, of course, means that lambda is equal to plus or minus I. And this is the super important point, which is that imaginary numbers are related to rotations. And we can see this by just looking at things in the complex plane. So multiplying by I is effectively equivalent to a rotation by 90 degrees in the complex plane. And let me draw this out. So let's say that we had a complex plane here. So let's say these are the real numbers, these are the imaginary numbers. Let's say 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So these are imaginary numbers, 1, 2, 3, minus 1, minus 2, minus 3, I, 2i, 3i, minus I, minus 2i, minus 3i. Okay? And so let's start by starting from the point here. So you can think of this as a vector. And when we take, what we do is if we take I times 1, that gives us I. And so that gives us this point. So we do list rotation. And we take I times I again, that gives you minus 1. That gives you list rotation. If you take I times minus 1, that gives you minus I, which gives you list point. And if you take I times minus I, that actually gives you 1 again. And we can try this for a different point as well. Let's try it for something a little bit less obvious. So let's take I times 2 plus I. So where's 2 plus I to begin with? 2 plus I is right here. So this is our first point. And what does this equal? This is equal to 2i minus 1, which is equal to minus 1 plus 2i. Minus 1 plus 2i, that gives you a point here. And so we are still doing the same rotation. Now if we do it again, I times, let's say 2i minus 1, that's equal to minus 2 minus I. So minus 2 minus I is here. And so that gives you list rotation. I times minus 2 minus I is equal to minus 2i plus 1, which is equal to 1 minus 2i. So 1 minus 2i, that gives you this point here. And lastly, if you do multiply by I again, why is I times minus I equal to 1? Oh, yeah, so if you have I times minus I, that is equal to minus I squared, right? Which is equal to minus 1, because I squared is equal to square root of minus 1, so this is equal to 1. Okay, but you still have the minus sign. So I is equal to the square root of minus 1. So I squared is equal to minus 1 is the important key distinction there. But anyway, going back to this, this times 1 minus 2i, this is equal to, well, I plus 2, which is equal to 2 plus I, and so you get this final rotation. So you have to be careful. I is not equal to minus 1. I squared is equal to minus 1. But sort of the point I'm making here is that multiplication by I is equal to this rotation in the complex plane, which sort of makes sense because that was the eigenvalue of this rotation matrix back here. So somehow, imaginary numbers are really closely linked to things that rotate. So now let's think about what happens when we multiply by 2i. Well, it turns out that we can think of this as two different operations. We can think of this as scaling by 2, and then you add a rotation by 90 degrees. Oh, sorry. And if we draw this out, I'm not going to label all the points again, but so we have the real axis here, and we have the imaginary axis. Say 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So if we had 2i times 1, so if we start out with a point here, 2i times 1, well, that's equal to 2i. Well, that's going to put us up here. So you notice that we've scaled by 2 and we've rotated. And if you do it again, so 2i times 2i, that's going to be equal to minus 4. Because I squared is equal to minus 1. And so that's 4 times I squared, which is equal to minus 4. And so then you go to here. And then when we do it again, you get 2i times minus 4, which is equal to minus 8i. And that gives you this new vector, minus 8i. And you can keep on going, but how did it become negative? So that's the super important point, which is that 2i times 2i is equal to 4i squared, right? And I squared is equal to minus 1. So this is equal to 4 times minus 1, which is equal to minus 4. No, I is the square root of minus 1. That is how we've defined I. Another way of thinking about it is that I squared is always equal to minus 1. That's just by definition. Anytime you see an I squared, you can replace it with a minus 1. If you just have a single I, you could replace it with the square root of minus 1, but you don't need, but like that might be confusing in places. So I squared is equal to minus 1. Well, that's the basic premise of complex numbers. Okay, so now like multiplying by I gives you a 90-degree rotation. What about other rotation angles? So we want to multiply by something, multiply the basis vector 1. We want something to multiply the basis vector 1 by that leaves you with something of length 1, because we don't want to do a scaling, right? So ideally we want to just have a pure rotation without any scaling factor. And so you need to multiply the basis vector 1s by something that has the correct angle. But of course, multiplying by 1 is the identity. So what we're really looking for is we're looking for some vector in the complex plane that has the correct angle and doesn't scale things. And it turns out that this is nicely captured by the unit circle. So this is, again, this is the real and the imaginary. So this is the complex plane. And let's see if I can draw a circle. So if we draw a unit circle, it's not the best circle, but it'll do. Where this point here is 1, this point here is I, this point here is minus 1, and this point here is minus I. Sorry, it's not quite a perfect circle. But if we do this, we can look at different points along the circle. So something like, let's say we have some point here, a plus bi, that's some value. And you'll notice that the length here is going to be 1 because it's along the unit circle. And this angle here is going to be theta. And so this here is going to be A and that's going to be B. And this triangle precisely gives you what complex number to multiply by to rotate by the angle theta. So if we redraw out this triangle, well, that's theta. This is 1, B, and A. And if you go back all the way to pre-calculus and learning about trigonometric functions, well, remember that sine of theta is equal to the opposite over the hypotenuse, which is equal to B, and cosine of theta is equal to the adjacent over the hypotenuse, which is equal to A. And therefore, A plus BI is equal to cosine theta plus I sine theta. And if you multiply by this complex number, so this is some complex number, you're going to end up with a rotation by the angle theta. Everyone with me so far? So let's give a couple examples of this. The first one will be the first one here is going to be the one we've already done. So what's a 90-degree rotation? So we already did a 90-degree rotation, right? Let's just multiply by I. Well, hopefully we get the same answer here. So what's cosine of 90 degrees plus I times sine of 90 degrees? Well, remember, it's often easier to think of these things in radians. And just as a note, 2 pi is equal to 360 degrees in terms of radians to degrees. So just you should remember that. And so therefore, pi is equal to 180 degrees, and pi over 2 is equal to 90 degrees. So this is equal to cosine of pi over 2 plus I times sine of pi over 2, which is equal to, well, what's cosine of pi over 2? 0. What's sine of pi over 2? 1. So 0 plus I, which is equal to I, which is, of course, exactly what the complex number we were multiplying by to get a 90-degree rotation. And now that we understand these sorts of rotations, well, we can try to find a 45-degree rotation instead. So let's say, what's a 45-degree rotation? Well, that's cosine of 45 degrees plus I times sine of 45 degrees, which is going to be cosine of pi over 4 plus I times sine of pi over 4, which is equal to 1 over the square root of 2 plus I times 1 over the square root of 2. And actually, this is quite interesting because this is, if we recall, we showed a little bit earlier that the square root of I is equal to 1 over the square root of 2 plus I times 1 over the square root of 2. And this makes sense because what we're basically doing is if we have, let's see, we have 1 I, and what we're doing here is we're basically saying, well, if we have this point here, which is 1 over the square root of 2 plus 1 over the square root of 2i, well, that is a 45-degree rotation. So if you multiply by itself, you get two 45-degree rotations, which gives you a 90-degree rotation, which gives you I. Okay, so I've been doing a lot of things. You should stop me if you guys have questions. In a moment, I'll have a couple questions for you to make sure we're all on the same page. So a lot of this should be stuff that you've seen vaguely before, like complex numbers are something you learn in pre-calc, but they don't really you don't always necessarily go into it in this much detail. Okay, but now note that we have some complex numbers that we can think about as rotations, right? And other numbers that we can think about as scalings. And it turns out we can, like with the matrices, matrix transformations, you can think of all complex multiplications as a rotation and then a scaling. So the length of the scaling is just what's called the modulus. Sometimes you call it the absolute value, but it's just the length of the vector a plus bi, which is, of course, going to be equal to a squared plus b squared, if we draw that out. So if we draw out this point a plus bi, well, of course, this side here is going to be equal to b, and this side is going to be equal to a. And so therefore, since this is a right triangle, the length of this thing here is a squared plus b squared. Or sorry, the Pythagorean theorem is the square root of a squared plus b squared. So the length of the scaling is the modulus. That's just the name we're calling it. And the angle of the rotation we call the argument. So it's the argument theta, which is equal to arg of z, where z is equal to a plus bi. And it turns out that, well, what we're trying to do is we're trying to figure out this angle here. And so the important point is that tangent of theta is going to be equal to b over a. Because tangent is equal to opposite over adjacent. Though you have to be a little bit careful, because if you're trying to figure out what theta is, so if a is greater than 0, then theta is equal to arctan of b over a. And if a is less than 0, then theta is equal to arctan of b over a plus pi. Because pi is equal to 180 degrees, and if we had the opposite number here, so if we had minus a minus bi, well, tangent of this angle, let's call it theta 2, tangent of theta 2 would be equal to minus b over minus a, which is also equal to b over a. So you have to be a little bit careful. You can't just take an arctan, because when you take the arctan, you might not get the right, you might be off by a factor of 180 degrees. But if you draw out the diagram, that will always get you the correct angle. Okay, that was a lot of material. Let's try it out. So, what is the modulus of minus 1 plus I? And let me reset the chat. I understand the tangent part. What is the a plus bi, etc. cosine mean? Sorry, let me go back for a moment. What is the a plus bi cosine? Oh, yeah, sorry, I didn't talk about it that much. So basically, that's another way of understanding it. So basically, when you take your original vector a plus bi, if you divide it by the modulus, if you divide it by its length, then all of a sudden you have something that's just of length 1. And so then it's on the unit circle, and then once you do that, that's equal to cosine of theta plus I sine theta. So that's entirely equivalent to this arctan formulation. This is a different way of writing it. Okay. But so remember that the, let me go ahead and write this down. The modulus of a plus bi is equal to the square root of a squared plus b squared. So what is the modulus of minus 1 plus I? Oh! Yep. Sorry about that. Here's the box. Someone should, the next time I do that, someone, yeah, you should tell me that I forgot to put the box up. Sorry, I have like 5 windows going, and yeah, no, it was completely on my fault. I have 5 windows, and I saw my box in one of my other windows, and it hadn't shown up in your window yet. But yeah, so what's the square root of what's the modulus of minus 1 plus I? Which of these is it? Okay, so let's see, what do we have? We have a lot of people who are saying D, and a few people who are saying C. More people saying C. Okay, well, let's just apply this formula. So when we do this, what is A and what is B? A is equal to minus 1, and B is equal to 1. So therefore, this is the square root of minus 1 squared plus 1 squared, which is equal to the square root of 2. So the answer here is C. Okay. Okay, it looks like this. Yeah, so about even, but yeah, you should make sure to remember the square root when you're taking these moduli. And let's try to do the next one now. So let me reset. What's the argument? So what's the angle? In terms of radians, so this isn't a little bit trickier, right? Because what you need to do is, well, you could do the arctan version, or what you could do is you could draw, what I like doing whenever I see one of these, oh, could I write out the argument formula again? Yeah, sure, let me go on to the previous page then. So the argument formula is over here. So you can use the arctan. So that's one way of doing it. I personally prefer to do it in a slightly different way, which let me go ahead and go back to this and show it. So I personally prefer to draw these things out and just look at the angle. So if we have minus 1 plus I, you're here, what is this angle? This is your, what is theta equal to? So you're going to have to go back to all of your knowledge of trigonometry. Okay, so it looks like we're getting B's. Yep. So that is correct. And the answer is because this is 135 degrees, because minus 1 plus I, that's the a 45-degree angle, and then plus the 90 degrees. And that's equal to 3 divided by 4 pi. So the answer here is B. Okay, so that wasn't so bad. You guys can see the next one here. Let me go ahead and reset. And, let me reset again. Yeah. And what about this third one here? So what about minus 1 plus I squared, take the modulus of lat? Okay, looks like we have started getting some responses. D's. Yep. Okay, so there are actually two different ways of seeing this answer. One of them is you can actually write it all out. So if we write this all out, this is the absolute value of 1 minus 2i minus 1, or because it's plus I squared. So this is equal to the modulus of minus 2i, which is just equal to 2. The other way to know this is that this is the length after you've done the square root of 2 twice. And so this is also equal to 2 because we've, this is just minus 1 plus I squared. Okay, and let's look at the last one, which is the argument of this thing squared. So what's that equal to? Okay, so it looks like we have a lot of people who are saying A, a few people who are confused, but, well, there are a couple ways of seeing this. One of them is that when you multiply something by itself, you're taking the angle, you're taking the rotation, you're doing it twice. And so the minus 1 plus I had an angle of 3/4 pi, and so therefore this is going to have 3/2 pi. How do you know if you need to use the plus pi or not? Oh, or if you're using the arctan formula, if A is greater than 0, then you use then you don't use the pi formula. If A is less than 0, then you do use the plus pi formula. Oh, yeah, this one is slightly harder because this one is just minus I. Well, this is one of the reasons why I usually recommend that you do it by just drawing it out. So the question is, what is this angle? And it turns out this angle is 3/2 pi. Because this is equal to the arg of minus 2i. Okay, So these are arguments and moduli of complex numbers. Basically, the moduli is just the length of the vector, and the argument is the angle it forms. And this is all a super long-winded way of getting to something fancier, which we're not going to prove yet, but we will prove it actually. We will prove Euler's formula a couple weeks from now when we get the power series. But Euler's formula, you might have seen it before. It's often considered to be... can you go over how you need to draw that out? Yeah, sure. Let me do that before. So basically what we had is you're always drawing it out, and you're always looking at where the point is. So our point here was minus 2i. Minus 2i is right here, right? Minus 2i. And so you just look at how long the angle is going counterclockwise from 1 to that point. Okay. But anyway, we have Euler's formula, which is this fancy thing, e to the I theta is equal to cosine theta plus I sine theta. This is one of the most beautiful formulas in mathematics. We will prove it in 2 weeks when we get the power series, but for now you can just take this as for granted. And, well, what does this actually all mean? So if you think about real exponentials, they define exponential growth. So e to the 0 is equal to 1, e to the 1 is equal to e, which is equal to about 2.7, e squared is about equal to 7.3. Well, imaginary exponentials, what they do is, as you can see from this formula, they encode rotation around the origin around the complex origin. So e to the 0 is again just 1, but e to the pi over 4 times I is equal to the square root of 2 over 2 plus I times the square root of 2 over 2. E to the pi over 2 times I is equal to I. E to the pi I is equal to minus 1. And the reason for this is because when we're doing these complex exponentials, by definition, for now we're just going to say by definition, e to the I theta is equal to cosine theta plus I sine theta. So we have these we showed earlier that a rotation by the angle theta is cosine theta plus I sine theta. Another really important fact is that that turns out to be precisely equal to e to the I theta. Oh, yes, can I please slow down and repeat? So, there is this really magic formula, which we're going to prove in a couple weeks, where e to the I theta, so if theta is an angle, and I is the imaginary unit, e to the I theta is equal to cosine theta plus I sine theta. And we're going to prove this with power series, but for now you should just accept this as true. And what it means is that when you take an exponent, when you take e to some real power, well, you're just increasing everything. You're just growing everything along the real line. Everything's getting bigger, right? When you take e to an imaginary exponential, to imaginary power, that actually encodes precisely this rotation around the unit of the complex origin. So so another way of thinking about it is that when you take exponentials of real numbers, you go in this direction. When you take exponentials of complex numbers, you instead go in you rotate around the origin. So this is complex exponentials, or sorry, imaginary exponentials. Exponent. And this here is a real exponent. Okay, so we all understand real exponential growth. Things just grow really, really fast. And so you get pushed along the real axis. As we were showing a moment ago, when you multiply by and that's because when you multiply by a real number, things get bigger. But now, one of the important things is that when you multiply by imaginary numbers, that encodes this rotation somehow. And so an exponent to an imaginary number is just a rotation around the complex origin. Any questions about that while we're still here? I will give you another couple examples in a moment. This is one of the most important facts about complex numbers. And Euler's formula, well, you should know it by heart, but I will give you Euler's formula on quizzes in the future. So I will give it to you, but you should know it by heart. Just because it is, by many respects, considered to be one of the most elegant formulas in mathematics. So basically, complex numbers create rotations. So you should think of imaginary numbers as creating... complex numbers can be both real and imaginary. So complex numbers allow you to create rotations and scalings at the same time. So if you think about it, real numbers just let you scale things to be bigger or smaller. Complex numbers, because they have this imaginary part, they allow you to both rotate and scale. But yes, that is the key to why complex numbers are so useful in many aspects of well, mathematics and signal processing and many other areas, which is that complex numbers allow you to encode these rotations as well as these sinusoids, as well as things that are periodic. And we'll see this once we get to go back to using this to solve differential equations. Yeah, okay, so now this gets us to something called polar form of complex numbers. If you are still confused by this, you should try looking up the things on Wikipedia about the polar form of complex numbers, because that's basically what we're introducing in today's lecture. So a complex number can be rewritten as a scalar. So z plus is equal to a plus bi. Well, that's in this sort of coordinate in this 2D plane. But you can think of it instead as a scalar and an angle. So it's a scalar because that's the length, and so that's how much you're scaling it by, and then you have an angle of rotation that happens when you multiply numbers by that complex number. Complex exponentials, on the other hand, are a little bit more complicated, but basically when you take a complex exponential, e to the a plus bi, you can break that up into e to the a and e to the bi, and then e to the a, well, that's just the length. So e to the a is the length because that is how much you're scaling it by, and the argument is just equal to b when you take an exponential. So multiplying by a complex exponential scales by e to the a and rotates by an angle. Sorry, there's a mistake here. I forgot my square root sign. That's important. Yeah. Yeah, whereas multiplying by a complex exponential scales by e to the a and rotates by an angle b in radians. Let me give a couple more examples, and then we'll finish with this first part of lecture. So, example, e to the pi over 4i. Well, this is equal to cosine of pi over 4 plus I times sine of pi over 4, which is equal to square root of 2 over 2 plus square root of 2 over 2 times I. And this is precisely a 45 degree rotation, e to the pi over 4i. Or another example, so we have e to the 2 plus pi over 4 times I. Well, we can break this up into two pieces. This is e squared times e to the pi over 4 times I. And you can continue rewriting this. So this is e squared times cosine of pi over 4 plus... what just happened? I went to the wrong slide. Plus I sine of pi over 4, etc. But basically what we're saying is that this is a scaling and a rotation. So let's have you all try it out. Let's have e to the 1 plus I, so I'll give you a pretty easy number. And I'm going to ask you a couple things. So first, what is the modulus of e to the 1 plus I? What is this equal to? So basically we're asking, what is the scaling factor? And remember, we had the scaling factor of... Okay, so it looks like people are answering B. A few people are answering C. Well, let's take a look at what the scaling factor is. So the scaling factor here, this is equal to, the scaling factor up here was e squared, right? So the scaling factor here is actually going to be equal to e to the 1, which is equal to e. So the answer here is actually C. Okay, well, let's try a different one. Let's try the argument of e to the 1 plus I. What's that equal to? And let me reset before you guys start answering. So remember the rotation angle here. The angle here was rotation by pi over 4. So the argument is the rotation factor, yes. Okay, looks like we were getting a couple B's in chat. And yes, that is correct, because this is going to be 1 radian. Oh, sorry, that's the wrong color. 1 radian. So the answer here is indeed B. And the reason for this is because we can write out this entire thing. E to the 1 plus I is equal to e to the 1 times cosine 1 plus I sine 1. And so the rotation's by 1, whereas the scaling is by e to the 1. And with that, I will go ahead and end the first half of lecture. When we come back in the second half of lecture, we'll talk about how we can use this to understand solutions to ordinary differential equations. So I will end my recording here.